David said, this is sort of taking a step back from sort of questions of bias and fairness and looking at kind of an overarching issue with prediction. Okay, this is based on joint works with Mina Jagadisan, Celestine Mendler-Dunner, Juan Carlos Perdomo, and Tiana Zernic, who've contributed to several different papers on this topic. And so the overarching theme of this talk is that the causal effects of algorithmic predictions are everywhere, and they touch on our lives. And many of the issues we're discussing related to algorithms and justice are about what algorithms actually do and how algorithmic decisions affect us. Okay? For example, we're interested in how recommendations and ads shape preferences in our consumptions, how selection rules incentivize individuals to adapt, be it either through gaming or self-improvement, how forecasts influence behavior and interventions. And there are many decision rules and risk scores deployed in this country and elsewhere that change life trajectories often drastically. Okay, so this is the backdrop of the talk. And what I'm going to do today is talk about these often invisible causal forces of prediction that shape populations, that shape our lives, and how to think about them, how to argue about them, and how to analyze them. And specifically, I will introduce a notion of performative prediction, which you can think of as a general conceptual framework that extends supervised machine learning in the direction of reasoning about sort of the downstream effects of predictions. Okay, I'll tell you about emerging results and their relationship to economic models. And then I'll transition into a closely related question of measuring power in digital economies and how you can use concepts from performativity to reason about how much power firms who deploy predictors have over us. Okay, and this notion of performative power, I think, or I will argue, is a useful complement to existing antitrust machinery. That works very differently. So I encourage you to ask questions, clarification questions. I'm sure we have enough time, and then there's, for more open-ended questions, we have a Q&A session at the end. But feel free to interrupt me if you have a question or anything is unclear. Okay, so let's review how we make predictions using machine learning. And this is, a general audience. I assume that, some of you are very familiar with machine learning, some of you are not. And fortunately, you don't need much about machine learning to follow this talk. You only need a couple of facts, really, right? And so the most fundamental fact to machine learning is that we represent a population as a fixed distribution, probability distribution, D, over data points, X and Y. Okay, so typically X are features that we have about an instance, and Y some kind of outcome or target variable that we would like to predict from the features X. Okay, so our goal in machine learning is typically to find a predictor, and I'll write theta X, that minimizes some kind of loss function on the distribution. Okay, and the loss function tells us how well we're doing in predicting the outcome Y from the features X. And there are all sorts of different loss functions here, prediction error and other things that are not going to be too relevant for this talk. Okay? But the fundamental thing that you try to minimize in machine learning is what is called risk. It's a function of the predictor and the distribution. And it looks at the average loss or the expected loss of the predictor on your population. So you average over the population, you look at your prediction theta X, and you look at how well that prediction is doing on Y, and then you average over all X and Y. Is that clear? This is about as formal as things will get. So if you understand this expectation, that's mostly, this kind of thing is mostly what we'll need. Okay? And so supervised machine learning you can think of as a field that has found all sorts of clever ways of coming up with these decision rules or predictors given a sample from the distribution. Okay, so most of machine learning is concerned with taking a sample, a large enough sample of data points from the distribution, and then fitting a model, a predictive model, to the data so as to minimize risk. Okay, and so when you're thinking about samples, the difference between the sample and the population is very important. That's often what machine learning people are concerned about. But it's less so it's not what we're going to be talking about in this talk. So I'm not going to be interested in the difference between sample and population. Instead, I'm going to focus on identifying and formulating problems with prediction at the population level. Okay, so things that are an issue even if you had like all the data in the world. Okay, so we're going to be talking about populations, and populations are sort of the central object of study and not samples. Okay, so you don't have to worry about sampling errors or estimation errors or anything like that. That typically comes up in this context. We're going to be talking about the underlying concept of a population. Okay, and so here's the first issue with supervised learning, and it's the fundamental issue that I'm going to be concerned with in this talk. Implicit in the supervised learning setup is that the prediction, theta x, cannot influence the outcome y. And it's kind of obvious once you think about it that way, but the reason is just that x and y are determined at the same time, right? You assume you have a fixed distribution over x and y, and so y, the outcome, is there when you sample x. Okay, they're both sampled, they're both created at the same time, they're both known at the same time. Okay, so if I sample from the data and then created a predictor, all the outcomes are already determined, so there's no way that my predictor can influence the outcome. It's just not possible in this setup. Okay, so supervised learning is what I call static, in the sense that nothing can influence this distribution. Okay, your predictor cannot influence the distribution of the data. That's just something you assume does not happen. Okay, in other words, in supervised learning, we ignore the causal effects of the prediction on the population. Okay, whatever causal effects the population, the predictor has on the population, it's not subject of supervised learning. Okay, so let me give you an example to make this more clear. YouTube watch time prediction. Okay, so as of a few years ago, when YouTube, was creating their, models for ranking content on YouTube, they predicted watch time. Okay. And so the ranking that you see when you open up YouTube on your cell phone is determined by a predictive model for watch time, roughly speaking. There's many other things at play, but to a first approximation, there's a predictive model that takes in features about the video and the user and predicts how much you're going to watch this video. Okay, and so that's theta x. It's predicted watch time, and y is the actual watch time. Okay, so this is a typical supervised learning setup, and you can use any supervised learning, deep learning thing that you want to do to find a good model for watch time. But here's the catch, right? So theta x, the prediction of watch time, obviously determines the on-screen ranking. Okay, so the ranking that you see, which thing shows up first, second, third, and fourth, and so on, is obviously determined by the score or the watch time prediction, right? So the actual watch time depends on the ranking. Right? So that's another way of saying that theta x, your prediction causally influences the actual watch time that manifests because you are ranking according to your prediction. So in particular, if you rank something, number 1 million, you're probably not going to scroll down until you see the thing that's ranked 1 million. Okay? So if you rank something very low, you're probably not going to see it. If you rank something 1, you're probably much more likely to watch it than something that you rank 2. Okay? So the prediction has a very strong influence actually on the data generating distribution. Okay, so supervised learning does not account for this effect, and it's kind of interesting that the paradigm that we use to build these predictors doesn't actually account for this somewhat glaring issue. And this is indeed like a major issue that other fields have reckoned with, in particular economics and finance, specifically in the context of policymaking. Where it's well understood that failure to take into account causal effects of forecasts and predictions is dangerous. A number of things related to this. For instance, Goodhart's law, which states that any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. So if you find some kind of pattern in your data and you try to exploit that for like policy making or control purposes, maybe like steering or like things like taxation or whatever, things are likely going to change. Okay. Closely related to that in the context of macroeconomics is Lucas' critique, which argued that macroeconomic policy can disrupt the statistical patterns that motivated the policy and hence lead to sort of unforeseen consequences. So if other fields have reckoned with us 40 years ago or longer, what can we do in machine learning to account for this issue? And so responding to this concern, we proposed this framework of performative prediction a couple of years ago, done at Berkeley, where we do the following. And this is what's called performativity. We postulate that when a firm like YouTube deploys their model theta, let's say their new watch time predictions, the population changes from what it was, let's call that D, to a new distribution d theta. Okay? So in the context of performativity, the distribution, the data generating distribution, is allowed to depend on the choice of the model. Okay? So it could be, at this level of generality, anything that follows from deploying your model. Okay, so it's a function of the model that you deploy, and as a result, the data is allowed to change given what model you deploy, and different models will induce different data generating distributions. This new distribution d theta is sort of meant to capture macro level changes to the decision, sort of a macro level change that's caused by the decision rule. Okay, so it's talking about the population level, and it's telling you how the population on the whole changes in response to decision rule. Okay, and so once you have this notion of d theta, okay, once you allow the distribution d theta to depend on the model theta, you can look at what happens to risk, the thing that you were trying to minimize in machine learning, okay? And you can just plug in this new distribution into your notion of risk the way you did before, where now instead of minimizing on the distribution that you observed at first, you're minimizing on the distribution that manifests from deploying your model, okay? So nothing prevents me from writing down risk of theta d theta as the expected loss of your predictive model on the distribution that it entails, okay? So this is kind of a moving target objective. It's saying that, you know, as you change your model, your kind of objective moves around, right? So it looks kind of like a hairy thing to minimize because the choice of theta influences what you're trying to minimize, okay? And that is exactly the issue in performative risk, okay? So this is called performative risk. And practitioners actually face this issue all the time, and they usually don't call it that, but they would say it differently. They would say that, you know, when you deploy a model, there's something like distribution shift, okay? So practitioners notice that when they deploy a model, things change, and then they have to retrain, okay? So typically in practice, when you're at YouTube, you would retrain your model every day or so because you know content has changed. And part of why it's changed is because you deployed a model, okay? So does that make sense? Good. So this is a simple extension of supervised learning to account for the effects that a decision rule has. Great. So what are we trying to do now? Okay, what are we trying to do once we define performative risk? The first thing we can try to do, and that's very natural, is to just minimize the performative risk over all possible models. Okay, just like in supervised learning, we try to minimize risk, we can try to minimize performative risk. So we can try to find the model theta star, which is performatively optimal in the sense that it minimizes the performative risk, okay? So it's just the minimizer of performative risk over all possible models theta. It is a complicated objective, it's a moving target objective, but we can write it down, and we can try to find new algorithms to minimize that. And we'll see some in a second. But there's actually another notion that is, you know, almost more natural in this context, which is called stability or performative stability. And we say that a model theta star is performatively stable if you optimize well on current conditions. Okay, so you keep the distribution fixed and you just optimize against what you see. Okay, so you know a performative a model is stable if you know the data that results from it, you know you're optimal on that data. Okay, so in other words, you're not, if you see that data that results from your model, you don't want to change the model. The model looks good to you on what you see, okay? So another way to think about this is that a stable point is a fixed point of risk minimization, okay? If you're, you know, YouTube, and you deploy a model, and after you deployed it, your model still looks optimal to you, like in the sense of minimizing loss, then you know you're at a stable point, okay? So a stable point is a fixed point of retraining in the sense that if you deploy a model, your model still looks optimal to you, okay? That's a stable point. So there are two ways to think about this that I find helpful. You can think of performative optimality as a notion of ex post optimality. You're trying to be optimal on what you get ex post. In other words, you're trying to be optimal on the distribution that you steer to by deploying your predictor theta, okay? So you're optimal on the thing that you get by deploying theta. That's what I call ex post optimal. And stability is ex ante optimal in the sense that you're optimal on what you see. You don't worry about what happens tomorrow, but you're optimal on the data you see right now, okay? So you can think of these as kind of like ex ante and ex post optimal, if you wish. Okay. So far, so good? Okay. Let's take this sort of line of thought a little bit further. There's no difference between steering, or ex post optimality, and you know, ex ante optimality. And let's think about this difference here. So suppose we're in a world given by a baseline state theta 0. Let's say that's the model YouTube deployed yesterday. And it gives us a distribution D that I can write as d of theta 0. Okay, so it's the distribution that results from whatever model that YouTube deployed yesterday. So here's a simple theorem I can prove, and I hope you're convinced that this is true. For the mathematicians in the audience, you might be able to find a proof here. But so basically, I can write the performative risk, okay, theta on d theta. I can write that as the risk, the ex ante risk of theta on d, the distribution I had, plus the difference between the performative risk and the distribution I had. Okay, so I can split it up in two ways, trivially. Okay, these are just, add up to the same thing. So in such a way that the first term is the ex ante risk, so that's how well you optimize on current conditions. And the second term is what I call ex post advantage. This is how much you can gain from steering to a different distribution. Okay? So to be good at performative prediction, there are two things you can do. One is you're good at optimizing against current conditions. And the other is you're good at steering towards a distribution that benefits you. Okay? And this simple decomposition tells you sort of exactly what the difference is between supervised learning and performative optimization or performative risk. The difference is that in supervised learning, the only thing you can do is optimize against current conditions. Okay? In performative risk, you can also steer towards a distribution that benefits you. Okay? And so this is what I call sort of what I want to highlight with this decomposition. There's how well you optimize on current conditions and how much you can gain from steering to a better distribution. Okay? So in the YouTube example, how much can YouTube gain from shaping consumption in such a way that it becomes more easy to predict? Okay? So these are the two levers you can pull. You can find sort of people's preferences, or you can steer towards a distribution where people become more predictable. Okay? So two ways to succeed. So let's keep this in mind. Performative risk equals ex ante risk plus ex post advantage. Optimization against current condition versus steering towards a better distribution, or one that benefits you more. Okay? So one of the first questions you might have about performative risk is how can we find stable points? How can we find points where we've reached a stable state, so there's no need for retraining. And I tell you that one thing you can try, and this is what practitioners would do, is simply repeat risk minimization. Okay, so you can simply repeatedly train and deploy models, which is the kind of loop you do anyway in practice. So you find a model theta that minimizes risk on your current distribution, and you deploy the model and you observe what happens. Okay, so this is basically just trial and error. Okay, so you find a model that minimizes risk on your current distribution, just via risk minimization. You deploy it, and you get some new distribution d theta, and you repeat. Okay, and from this fact that I showed you earlier on, you know that if this ever converges, you're at a stable point. Okay, because stable points are fixed points of retraining. So if this ever stops, if you're no longer moving, then you've reached a stable point. The question is just if it does in fact stop, right? Okay, does this actually get to a point of stability where you no longer feel like you have to update your model? Okay, and the answer that I found in a couple of years is that in fact that's true under some assumptions, under some optimization assumptions. Specifically, if your loss function is strongly convex and your distribution map is not too erratic, so this distribution d theta depends only on this model theta in a controlled way. So it doesn't flip around too much when you change theta. It's, in other words, Lipschitz in the model parameters theta. Then this method of repeated risk minimization finds a performative stable point. Okay? So there are ways of finding stable points. We can using repeated deployment and optimization, find points that are stable. Okay? So that answers one question. We can find stable points. And without strong convexity, there's, anything can happen, and somehow what happens is kind of unclear. It's not even clear that you would converge to anything reasonable. Okay, so this first result sparked a lot of work on performative prediction that you can look into. So there are many extensions of this at this point. The one you just saw is when retraining converges to a stable point. We extended this to stochastic optimization. So what happens if you have finite samples? Sometimes you can find even performative optimal points. People have studied the case where your distribution actually changes slightly over time, so it's not all at once, but let's say you have some kind of time series, and every day your model changes a little bit. And there are settings where you have multiple predictors that are also steering in different ways. Okay, but if you're interested in this technically, it's still like an area that's rich with open problems. So there are many things I don't know, specifically what happens for non-convex losses and very large models and so on. So there are many questions in this area that you can look into if this is something that excites you at a technical level, okay? But I want to make a slightly different transition, okay? And I want to sort of think a little bit more about where this distribution comes from. Okay, so in performative prediction, we assume that your model causes some distribution to manifest. Okay, you deploy a model theta, and you get some distribution d theta. But where does that distribution come from? Okay, so where do we get this population level dynamics that tells us how theta leads to d theta? We saw these results for finding stable points, but what assumptions can we make on the distribution d theta? What is a reasonable assumption on what this distribution should look like, and how might we be able to say more about the distribution, okay? And specifically, taking sort of slice from economics, I want to ask, can we derive this distribution d theta from sort of micro assumptions about the behavior of individuals, okay? And this is analogous to what's called microfoundations in economics. It's this idea that your forecast should be consistent with the principle of microeconomics, okay? So when you make, let's say, a macroeconomic forecast, it should be consistent with the fact that, you know, or with the assumptions about individuals that they're strategic and they optimize and they're rational and so on, right? So can we somehow derive this, you know, distribution from assumptions about individuals? And the answer is yes, and that leads to a whole set of other results on this problem, which came out of this research area called strategic classification that's been going on actually for longer than performative prediction. And so here you assume that this distribution d theta comes from strategic behavior of individuals who are trying to adapt to your decision rule. Okay, let's say YouTube content creators who observe the new ranking and try to change their content in such a way that they get ranked high. Okay, so you assume that somehow at the other end of the firm are a bunch of market participants who are responding strategically to your decision rule. Okay, and so the standard assumptions that you make in microeconomics or standard microfoundations is that you assume you have a rational and utility maximizing agent. So you have a YouTube content creator who tries to change their videos so as to optimally respond to YouTube's algorithm. And you assume that sort of all individuals strategize alike. We're all alike in how we're selfish. And so there's a single agent that's representative for the whole population. Okay, so you can sort of summarize the whole population by the strategic behavior of a single individual. And this individual, this agent, computes kind of the best response to the decision rule. Okay, so it's kind of like the utility maximizing change in their behavior or features in response to this decision rule. Okay, so these are the three assumptions that you can make, and they give you like a really interesting way to come up with these distributions d theta and to actually say what they are. So rather than saying there's like abstractly some distribution d theta that comes from your model, you can actually say how it came about, right? And you can put your finger down on like the mechanism that created the distribution. Okay, so this is the route taking in this research area. I've seen lots of work on in the past 5 years. And so the advantage of these assumptions is clear, right? So now you have like a very specific understanding, a very detailed understanding of this distribution, okay? So you know exactly what happens in response to your decision rule. And as a result, you can even find optimal points, okay? So you can find what's called performative optima, or what's called Stackelberg equilibria in this setting. So these are performative optimum points, so optimal solutions, okay? And you get that because you now know exactly what the distribution looks like, okay? There are many extensions, varying agent costs or utility functions, different model families for the classifier, what happens if you only approximately compute best response or have partial information and so on, multiple different cost functions. Again, lots of results in this area that people have come up with in recent years, okay? So the thing you should take away is that this research area strategic classification is what happens when you instantiate performance prediction with standard economic microfoundations. So you assume that the distribution that you get comes from the utility maximizing behavior of strategic individuals. Okay, so it's like a nice way to summarize the connection between these two areas. Okay, but there are also shortcomings of these standard microfoundations that I want to highlight, so they're not like something you should necessarily be happy with. First of all, the aggregate response, d theta, that comes from these, from these assumptions, has these kind of discontinuities. So the distributions that you get will always look very unnatural. So there's like a threshold theta, and everyone within some interval of this threshold will move up to the threshold, but everyone else stays put. So the distribution d theta will always look like this kind of shape, which of course is not very natural. You sometimes see this, but most often you don't see that, okay? What's even more concerning is that as soon as some individuals choose not to be strategic or are unable to be strategic, any positive fraction of non-strategic agent destroys the existence of performative stable points. So you can see that as soon as you have like any fraction of non-strategic agents between 0 and 1, retraining would oscillate. So you get this kind of like oscillating behavior of retraining. And that's actually something that Björkegren and Blumenstock observed in a very interesting experiment in the context of microlending apps, where they saw in practice or in experiment, in a field experiment, that you actually do get this kind of undesirable behavior if some people are not strategic. Okay, and usually you have people who are strategic and some are not strategic. And third, what's even more concerning about these solutions from a normative perspective is that these assumptions lead to solutions that maximize a negative externality called social burden. Okay, and so basically what is social burden? It is the expected cost that positive instances, in this case the green instances, pay in order to be accepted. Okay, so if you deploy these kind of models, what happens is that anyone within the decision boundary, this black line, has to move above it, even if you are a positive instance. So even if you're somebody who should be accepted by the classifier, you now have to work or expend cost to be accepted. And in fact, the optimum solution maximizes that cost to the individual. Okay? So these are kind of solutions that are optimal for the firm, but they're sort of most strenuous and undesirable for the individual. Okay? So it's a very one-sided solution that benefits the firm a lot more than the individual. Okay, so let's come back to performativity and wrap up what we saw so far. Okay, so I argue that once you know this concept, if you go out of this talk and you look at your favorite problem out there, I'll argue that you see it everywhere. Okay, it's just something that is ubiquitous. In fact, I've convinced myself, and you can try to refute me, that any social prediction problem is performative. Okay, so if you find some prediction problem in the social world that you think is not performative, come to me and tell me what it is. Because I think in the social context, the point of prediction is to be performative. Okay, you wouldn't bother to make a prediction if you weren't trying to change something. Okay, so it's almost like a tautology. Okay, and so what we saw is that performative prediction gets at the difference between learning and steering, optimizing against current conditions and steering towards a distribution that benefits you more. Okay, and this was the simple decomposition of ex ante risk and ex post risk, or ex post advantage. So how's this related to what I call the invisible hand of prediction, right? So if social prediction is performative, right, the question still remains of how much, right? If I make predictions from the convenience of my office and nobody's listening, probably not very performative, right? If the Fed is making a prediction, probably highly performative, right? So it depends on who's making the prediction. And to be a little bit more clear, the strength of performativity depends on power. It depends on the power of the entity that is making the prediction. Okay, and this shouldn't surprise you because here's one dictionary definition of power: it's the capacity or ability to direct or influence the behavior of others or the course of events. Okay, so it's intuitively clear that power and performativity should be related, because how much you can influence things is how performative you can be is a matter of power. Okay, so thinking about this, you can try to turn this on its head, and you can ask if you can use performativity to measure power, okay? Rather than saying that, the amount of performativity depends on power, you can say, let's try to get a sense of how powerful a firm is based on how performative it is in any given prediction setting. Okay, specifically, you can try to sort of get some insights about this, highly debated question of like, when does a digital platform have monopoly powers or too much power over its, consumers? Okay, and so digital platforms are a tricky case for current antitrust frameworks. Actually, a very tricky case, and that's demonstrated by two major reports that came out in 2019. One from the Stickler Committee on Digital Platforms. It's 100 pages long, it makes many points, but in particular, it says pinpointing the locus of competition can also be challenging because the markets are multi-sided and often ones with which economists and lawyers have little experience. This complexity can make market definition another hurdle to effective enforcement. So one major issue is that you don't really know what market a platform is operating in. Is it media? Is it advertising? Is it entertainment? Is it something else? Who are the competitors? Who are the competing firms? Who are even the customer? What are the prices? What products are being sold or consumed? And there was a report by the European Commission, also about 100 pages long, published at the same time, which calls for less emphasis on analysis of market definition and more emphasis on theories of harm and identification of anti-competitive strategies. Okay, so I'll try to respond to these concerns using concepts from performativity and show you how the notion of performativity can be used to identify potentially anti-competitive strategies. Okay, and this is something we call performative power. It's a notion that's inspired by performative prediction, and the informal definition is fairly simple. Okay, I'm going to make it formal in a second, but the informal definition is performative power is the largest change to a population that a firm can cause with respect to a given set of actions. And the action set is typically the set of models you can deploy. Okay, so if you're in a prediction setting, let's say YouTube again, is a set of ranking models that you could deploy. Okay, so let's think about this one more time. Performative power is the largest change to a population that a firm can cause with respect to a given set of actions. Okay, so how much can you influence or steer a population with the predictions that you make? So notice that when I go about it this way, there's no need here for a market definition. There's no need for knowing what a firm is, what prices are, what equilibrium might or might not attain. None of that is relevant. I sort of look directly at where rubber meets the road and look at how much can you actually change a population with the algorithmic models that you deploy. Okay, so I'm going to try to jump directly to measuring things or measuring causal effects of your algorithmic models. Okay, and so this is a very different route from what's taken in traditional antitrust machinery or frameworks. And so as a result, could be a useful complement. And I'll try to tell you why it sort of checks a number of boxes. Okay? But let's walk through an example. I'm going to make this definition more formal. And I think it helps to first give you, again, a slightly informal example about Yelp reviews. Okay? So are people still using Yelp? I don't know. People still are. Okay, yeah. It's probably no longer as widely used as it used to be. But here's, if you remember what it is, it's like a website that ranks restaurants, and it gives out star ratings. And these stars are discretized in half-star increments. So there's a difference between 3.5 and 4 stars. And so the way you would apply this to, let's say, Yelp reviews, or Yelp ratings, rankings, I should say, is that first you choose a population of units that you think are at one end of the power relationship. Okay, so sort of the locus of where you expect harm. Okay, and in this case, let's choose restaurants in the United States. And now you model actions, and I call the action set capital F, that are within reasonable agency of the firm. Okay, and I'm going to say these are all the ranking models that Yelp could deploy. Okay, so let's ignore how exactly we formalize that. But these are all the models that Yelp could use to rank restaurants and give out these star ratings. And so now what I have to do is I have to put my finger on a feature of interest for each restaurant in the United States. I call that Z of U. U is a restaurant. Z of U is a feature I care about. Let's say the wait times at the restaurant, okay, as a measure of how well the restaurant is doing, how busy it is, how much business it's getting. I look at the wait times ZU at the restaurant U, okay? And so now, here's the trick, okay? So you consider the potential outcome, ZFU, of the feature of interest under the hypothetical action F, okay? So I look at the counterfactual wait times at the restaurant U if Yelp were to deploy the ranking model F, okay? So I say, what would happen counterfactually if Yelp deployed some other ranking model F, okay? And specifically, what I'm interested in is how that affects wait times, okay? In other words, how much can Yelp influence, the well-being of the restaurant by a change to its ranking algorithm? Okay, so I take the CU as a measure of well-being in this example, and I look at how much you can influence that in the population of restaurants by a change to your algorithm. And so, how do we choose F? In the definition that I'm going to put forward, we're going to try to find the action F that maximizes this change. So you, as the investigator, have a lot of freedom here. You're allowed to sort of construct cleverly some kind of model or experiment where you think this maximizes the difference between wait times that would result from deploying this model or this action. Does that make sense, this example? Okay. So let's back out like a formal definition from this example, and it's not hard. This is the formal definition of performative power. You fix a population of units or participants interacting with a firm. This could be restaurants in the Yelp case. It could be YouTube content creators. It could be Facebook users. You fix a set of actions, call it capital F, of actions that a firm can take. This is typically, a set of models that the firm can deploy, but the definition is more general, and that's sometimes helpful. And you have to fix features or data of the participant U that you're interested in, and typically you would choose features that make sense for the investigation that you're making. So if you were talking about consumer welfare, you would try to pick features that let you estimate user welfare. And so the definition needs this potential outcome variable. So if you know about causal inference, you know what a potential outcome is. This is something you can define. It's a random variable that tells you, what the data of the participant U were if the firm, or would be if the firm were to take action F. Okay, so it's a causal counterfactual notion. What happens if the firm takes action F. Okay, and so then the definition of performative power of a firm with respect to the population, the action set, and the potential outcomes is simply the supremum over all actions of some kind of distance between the feature ZU and the counterfactual feature ZFU. Okay, and here distance is just a metric over the space of data points. In my example of Yelp, it was just the absolute value. You could pick something else here if you had multiple features or higher dimensions. This is up to you. It depends on what you're trying to do. But this distance doesn't have to be super clever. So if you have a single feature, it could just be the absolute value. And the expectation is taken over random participants, so you average over all the participants U, and the randomness that may be in the potential outcome if there is uncertainty in what happens. Okay, so you can think of this as some kind of like treatment effect. Okay, so you look at what happens under this hypothetical action, but you look at the largest possible change over the action set. Okay, so this is the formal definition. I'm going to tell you in the remaining time that first of all, it has properties that make it, I think, a good measure of power. And second, that we can estimate it empirically using observational causal designs. Okay, so let me start with a key property. Was there a question? Or okay, let me start with a key property. What happens when you have low performative power? What is kind of the state of low performative power? So low performative power implies that the best the firm can do is ex ante optimization on current data. There's no gain from ex post optimization. So low performative power corresponds to the situation where the only thing the firm can do is optimize against current data, and there's no way they can steer the distribution to something else that they would prefer. So in that sense, the firm's kind of like a price taker. They have to optimize against the data that they see, and they have no ability to influence or steer towards data that they would prefer. Okay? That is what low performative power means. You can make this formal by looking at the following. Suppose, again, the world is in a baseline state theta 0 that gives us a distribution D. And let's say we do supervised learning, call that theta SL, which is the risk minimizer on the distribution D that we currently see. And let's say we contrast that with the performative optimum, which is the risk minimizer or the minimizer of performative risk, where I minimize risk on the distribution d theta. Then I have the following relationship. The risk of the supervised learning solution is upper bounded by the risk of the performative optimum plus performative power. So in other words, there is no way that I could, get a gain from this performative optimum. Okay, so so how should you think about this? So if there was a gain to the ex post optimum, then you would think that the right-hand side, the risk over here, the risk of theta PO, would be much smaller than the supervised learning solution. Okay, so this lower bound tells you is that the performative optimum is no better than the supervised learning solution up to the performative power. Okay? So again, I want you to think of this as analogous to price taking. The market gives you data, and you can only optimize against this. This is what supervised learning says. And the right-hand side, being performative, doesn't help you much. Okay? So if performative power is 0, then actually you cannot get any ex post advantage. The best you can do is supervised learning. Okay? So if your performative power is 0, then supervised learning is the best you can do. Okay? So performative optimization would be no better than supervised learning. So that's a general property that follows from, that follows from in generality. So, there are no assumptions here. If you set up this definition, then this is what follows. And it gives you kind of a nice interpretation of performative power using this idea of ex post and ex ante optimality. Okay, so there's no ex post advantage if your power is small. Okay, the only way if you can get an ex post advantage is if you have high power. You can take this one step further and you can look at what happens to performative power in strategic classification. So if you're willing to make these more specific micro assumptions that we make in strategic classification, can we say more about performative power? And the answer is yes. Okay, so you can argue that in fact in this setting, a monopoly firm maximizes performative power. So if you're the only market participant, you have the maximum performative power. Second, and so participants in this case are willing to incur a cost equal to the utility for the service. What this means is that, if YouTube were the only video streaming service and it suddenly decided that all videos have to be at most 10 minutes, okay, then you would see that all the content creators would respond by cutting down their videos to 10 minutes, okay? So there'd be no way for them to say, okay, screw this, I'm going somewhere else, okay? So you have the largest performative power if you're a monopoly firm. Second, performative power decreases in the presence of outside options. So if there's indeed something like Twitch where you could go instead, then you might say, well, wait a minute, I'm not going to re-edit all my videos to be less than 10 minutes. I'm actually going to swap to this other service. Okay? And third, when platforms compete over users with services that are substitutes, perfect substitutes to each other, then already two firms lead to zero performative power. Okay? So if now users sort of dynamically choose where to be, where to home, based on who's better for them, right? Then even two firms lead to zero performative power. And if you know sort of classical econ stuff, this is analogous with the well-known Bertrand competition, okay, which says that if two firms simultaneously set prices and users can choose between them, then the firm that sets the higher price gets none of the business. Okay, and so the equilibrium solution is where both firms set prices at no profit. Okay, so that's the Bertrand competition, and you recover this result using performative power in the context of prediction. Okay, so if you have two firms that are competing with perfect substitutes, even two firms already lead to zero performative power. So you can see how performative power sort of has the look and feel of a measure of market power, but it doesn't need any of the notions. You don't even need to know who are the firms involved. You can just measure it. You don't need to a priori set up the market and talk about equilibria or anything like that. But if you do that, you can see that it recovers the right kind of relationships. Okay, so let's see how we can estimate this in practice, right? How would we go about applying this? And in particular, how would we go about estimating performative power using observational designs? Okay, let's go back to our example of Yelp. And there was a paper from in 2012 by Anderson and Magruder, which argued using some regression discontinuity causal inference design that an extra half-star rating causes restaurants to sell out 19 percentage points or 49% more frequently. Okay, so in this case, how quickly you sell out is a measure of how much business you have, how well you're doing at a restaurant, and an extra half-star rating gives you a 50% advantage. Okay, you sell out 50% faster if, or more frequently, if you have an extra half-star rating. So you can look at this, and there are many results like this in economics, which have these kind of causal effects of various algorithmic changes. What does this have to do with performative power? Does it have anything to do with performative power? And I argue that it does, and you can actually use these kind of things to lower bound performative power. So remember, and this is where the supremum comes in, right? Remember that performative power was the supremum or maximum of all actions that the firm can take of the distance between the data and the counterfactual data under that action. Okay? So here's the trick, here's the idea. You can take this action F to be Yelp's action by which you swap all the restaurants that are near the 3.5 star threshold. Okay, let's say there's some score threshold at which you get 4 stars instead of 3.5. Now what you can do is you can swap all the firms that have very similar scores and swap whether they come out with 4 stars or 3.5 stars. So you randomize around all these like discontinuities, the star discontinuities, and you swap firms that are very close to the threshold. Okay, and so now take ZU, again, to be the feature that was studied here. So let's say number of customers or how frequently you sell out. And so now, under this action that we just constructed, this randomization or perturbation around the half-star thresholds, you see a huge spike in that feature, or a huge change in that feature, right? Because the people that got randomized, the people that got 3.5 star, versus 4 now get much less business. The people that got, or the restaurants that got 4 stars instead of 3.5 now get much more business. Okay, so you're going to see a huge spike, a huge response in this variable under this hypothetical action. Okay, so this is the idea. So you take some empirical information, in this case, this estimate from this paper, and you can back out, a lower bound on performative power by saying that, I'm constructing this hypothetical action corresponding to the experiment that they ran, and then I see how much things change, okay? In fact, this approach is very general once you think about it. We call this display discontinuity design, and it applies whenever, a recommender system or an online platform displays scores discretely, which is almost always the case. Usually there's some predictive model that has a score, and that score gets, rounded into buckets. It could be stars, or the ranking position on YouTube. It could be the display positioning, the ordering, the coloring, as in Rotten Tomatoes. It could be all sorts of discrete information that the platform displays. And there's always the step from a continuous score to a discrete display, okay? And so any causal effect of such a display discontinuity can be converted into a lower bound on performative power, okay? So whenever you have an experiment that tells you, oh, the YouTube video ranked number 1 gets like 50% more views than the YouTube video ranked number 2. You can construct a hypothetical action which will use that to lower bound performative power. Okay. And the idea is always that you take the platform's action so as to swap or randomize items right around the discontinuity. Okay. And this gives you sort of a general recipe for turning empirical information or experimental information into lower bounds on performative power. Okay, so I would argue that it's actually empirically a fairly tractable approach to lower bound performative power. So let's wrap it up. I'm pretty much out of time, and I'll leave time for questions. What's different about performative power compared with other measures of power? Classical antitrust tools need market definitions. Sometimes you need an equilibrium notion to compare to. And you sort of hardwire a notion of competition, into your, or the market definition comes with a notion of competition, okay? And so performative power instead needs a population definition. You don't start with the overarching market, you start with the population where you think harm or, anti-competitive behavior might occur, okay? So you start with the population, you start where rubber meets the road. And the investigator will specify units and features where she suspects power to manifest, okay? So things where you expect that something is happening. And then the interpretation of the features determine whether power is harmful or not. And there's an important difference between power and harm, okay? There could be high performative power because your product is actually the best and everyone switches to your platform. So not all performative power is harmful. And whether or not it is depends on the features that you chose, okay? And this is what you would expect, okay? And so what you would argue is that low performative power is kind of a conceptual alternative to, or alternative notion to competition, okay? Rather than deriving what is competition from a market definition, you say that competition is the state where firms have low performative power, okay? So the state where firms are unable to steer the population, and typically that is because other firms would jump in and there are outside options, and the moment you try to steer, people come in and take your business. Okay, but you don't need to know this. You can just define it without knowing anything about the other firms. Okay.